So first of all, I want to point out I wore a check shirt, talking check. That's my stupid joke. You've all seen me present. If you've come to this before, if you haven't come present, I like to get a little interaction with the audience. So the first thing I need to do is everybody needs to stand up. Okay, please read out loud all text that is in. I hope I got the check right there. You know, I hope Google Translate got the check right. Okay, so we're going to talk about Goldilocks and the Three Bears. Okay, as a Boston accent, every time I told people Goldilocks and the Three Bears, they thought I was pronouncing beers. But really, we're going to be talking about Goldilocks and the Three Bears. Okay, and notice I say it in the same way. Hopefully that doesn't start. How many people here know the story of Goldilocks? How many non-Americans and non-English know the Goldilocks and the Three Bears story? Okay, because I was very, how many people don't? Okay, so that ruins my entire presentation. But so it's a children's story in America and I guess in England, and I saw England's part of Europe at least for 2 more weeks. So some Europeans know about it. So let's. To give you a quick introduction to the story, we'll see if this will work.
Goldilocks and the Three Bears. Once upon a time, there was a little girl named Goldilocks. She had golden hair. One morning, she was walking in the forest and lost her way. She saw a friendly cottage. Wow! She knocked on the door, but nobody was there. She went inside. The friendly cottage belonged to 3 bears. Goldilocks was very hungry. She saw 3 bowls of porridge on the table. First, she tried a spoonful from Daddy Bear's big bowl. This porridge is too hot. Next, she tried from Mama Bear's medium bowl. This porridge is also too hot. Finally, she tried from Baby Bear's small bowl. This porridge is just right.
Okay, we're going to advance here. Oops. Oh, boy. This worked fine online. I downloaded it. Just let it play through.
And she ate the whole bowl. Goldilocks was tired. She saw 3 chairs kept in the room. This chair is too big. This chair is too big too. This chair is just right. But the chair broke. Goldilocks was very tired, so she went upstairs
Okay, I think you got the basic clue. Okay. So the basic idea is, in America and in English now, they talk about the Goldilocks planet, for instance. So a Goldilocks planet is a planet that is close enough to the sun, but not too close so it doesn't get too hot, and far enough for, not too big, so they call it the Goldilocks planet. The basic idea is the Goldilocks is sort of the perfect, not too hard, not too soft, right? The middle ground. We have the 3 bears, we have the too hard bear, we have the too soft bear, and then we have the baby bear who tends to be just right. So what's this got to do with security? Well, I'm going to be talking about security here. Most of the security that we have in containers, I would say, is Goldilocks, right? It's just right. It's sort of in the middle. But the problem with that, so we'll be covering that, and I'll be going through different topics about security. But I would like to crank up the security, right? Get more secure in the systems. And we have all the tools to do it. The problem is, how many people in here ever turn up the security? How many people in here have ever done cap drop? Okay, I see 3 or 4 liars in the crowd. Okay, how many people do this? Run privileged. Okay, a lot more people telling the truth, but there's a lot of people who didn't raise their hands who are lying. Okay, so basically, how many people did this? Not me. So the basic, most times people are, my application's more important than security, right? That's the way they think. So most of the time they're turning down security. So if all of our security is Goldilocks, how can I get better than Goldilocks, right? How can I go from Goldilocks to Papa Bear, right? How do I move people over to that? And that's what we're going to be looking at today in this talk. Okay. So first of all, you might have, if you follow me on Twitter or stuff, I went a lot against the big fat demon. And I'm going to explain one of the things we've done to move towards the Papa Bear for the big fat demon. The problem with the big fat demon is if every manner of interacting with containers goes through one root running daemon, then you get the least common denominator of security. Okay? So the basic idea, if you're doing, in my opinion, when you're running containers in production, say underneath Kubernetes, you have one set of security goals. When I'm building containers or building container images, I might have a different set of security goals. If I'm running and playing with containers, I have yet a third security goal. So let's look at, so that's really what we were doing when we created the set of products, Cryo, Podman, Scopio, and Builder. Cryo, again, is running containers in production, right? You don't want limited privileges. You don't want people just going in and fooling around in your Kubernetes environment. Podman's for playing containers, sort of, experimenting, designing containers. Scopio is really just about moving container images around, right? It just moves them around the environment. And then Builder is all about building containers. Each one of those has different security goals. So quickly, let's look at container images. So everything sits at a container registry. That's a container image. And in the container image is really where the developer defines what his application is. So to think about it, when I'm designing a container image, I am putting in all of the knowledge I have about how I want my application to run. So in an OCI image format, there's a tarball that includes the image. So basically, it's a root fs tied up. And then there's this JSON file associated with it. That JSON file usually says things like, what is the entry point? What are the environmental variables? What's the executable I expect you? What is the working directory? And then it has a bunch of labels and some other fields with it. But basically, that's where the developer defines what he wants to do when he wants to run a container. So if I'm going to run a container, the developer has some input into me running the container. The next thing that has input into running a container is the container engine. Okay, and the container engine has hard-coded constants into it, right? Basically, it decides things like what SELinux label, what are the C groups, what are the namespaces. All that stuff is hard-coded into the container engine that you're going to run against. Okay, so that basically has input in how do you run a container. The last thing that has input into running containers is the human beings that are launching the containers or an orchestrator like Kubernetes, right? So basically, when I want to run a container, I'm going to specify, I need these additional volumes in. Then it's going to take the container engines, the hard-coded constants in the container engine, assemble those together, and then it's going to take what the developer's thoughts of the image that I'm loading, and it basically combines all three of those things together and creates a JSON file. And that JSON file is called the OCI runtime specification. So when a container engine launches a container, it writes out this OCI, which is a combination of those three inputs, and then launches a OCI runtime, like run C or crun or Kata containers or gvisor, and that launches it. But if we go back here, if there's only one container engine, then you only have one way of hard-coded constants. And so if we basically look at the other container engines, now I can have different constants in the environment. So by doing this, by basically making cryo sort of separate, I can put different hard-coded constants into cryo and force you a little closer to the Papa Bear moment. And that's really what the goal here is with doing this. So let's look further into this. So I wrote a blog. I don't know how long it is. I can't read it. Basically, a few years ago, called Just Say No to Root. Okay, how many people here run root running containers? Okay, and the rest of you are lying. So most containers in the world don't need to be run as root. If you think about it, really the only ones that need to run as root are applications that are modifying the kernel, right? It really, if you're an administrative tool, you have to run as root. But almost every other application in the world will run without root. But because of the way we install software and develop software, we actually give you the impression that you have to run, right? Red Hat is in Fedora and Debian. Everybody built packages that goes into containers as if they were going to VMs. So the assumption's built in that application start as root and then drop privileges. But basically, you can turn that on head and not have to do that. The problem here is some applications do run as root, and when they run as root, one of the core technologies of Linux that we use to protect root is by subdividing the power of root into capabilities. So right now, when you run containers, the default way you run containers on your system, if you're running as root, you are using 14 out of the 37 Linux capabilities. So these are things like set UID, set GID, so you can change UIDs inside of your container, kill, so you can kill processes of other containers. But anyways, so these were originally defined by the upstream Docker project, these 14 capabilities. And how many people in here could name 14? Okay, that's because it's hard-coded into the Docker daemon. I'm going to show you what they are. So these are the 14 capabilities that everybody that runs containers, whether with Podman or Docker, is getting by default. So let's look at a little history here. Audit write. This, when you log into a system, the login program writes a file called varlog and procsys login UID. Login UID then records the UID that you logged in the system. Every process you start from that point on goes in. In order to do that, you need audit write. How many people think that you should have your containers writing to the audit system to say a user is doing something? So why is that capability on by default? The reason that capability is on by default is 8 years ago, when Docker first started, everybody thought that containers were VMs. So they put SSH daemon into the containers. And when SSH daemon does, when you log in, if you SSH into your container, the container attempts to write to the auditing, to that, that's proc / sys login UID, and that requires audit write. SSH daemon blew up, and everybody said, this sucks. I can't log into my container. So at that point, somebody upstream said, we'll just give audit write by default. How many people here run SSH daemon inside of their containers now? Very few, okay? I would say no one should, but, right? But here we are 8 years later, and we've never taken that away. Make node. When I run a container with make node, that means I can create device nodes in it. That's a capability that allows me to create device nodes. Almost no application in the world creates device nodes. Device nodes, when you run a container, are automatically created for you, but we allowed make node. You know what the history of that is? There was an Ubuntu package that when you installed into Docker, it would go out and create a device node. When you're doing an RPM apt-gets, it would install and create a device node. It blew up. So somebody said it's a good idea to do make node. Now, make node is protected by other capabilities and stuff, but I think we should just get rid of it altogether out of there. Sys-chroot. Sys-chroot allows you to create a chroot for running an application inside of it. But if you're in a container, you're already in a chroot. So the only reason I can think of this one coming on is because somebody installed bind chroot inside of a container and it blew up, so someone said, well, let's just allow that. So these are the reasons, the only reasons I can think of that these are allowed by default. So the last one is netraw, and this is probably the most dangerous one. Netraw allows you to create a packet on any kind of TCP or IP packet and send it out on your virtual private network. It has been shown a couple of times to break out of virtual VPNs. So all these people providing VPNs, well, if I am able to format a certain packet and send it out on the wire, I might be able to get to the host network instead of being inside of a VPN. Why do we allow netraw by default? For ping. Okay? Ping creates an ICMP packet and has to send it on the network. So by default, we're allowing this really dangerous capability in the system, and I'm going to show you what you can do. Okay, so this is going to be a demonstration of dropping capabilities. Well, dropping capabilities prevents the ping command from working, and this is a demonstration to show that. So here we are, we're just running a container, a pre-created container that just has the ping package in it, and it goes off and it sends pings. Beautiful, right? And that's using default capabilities. But now I'm going to do the cap drop. So I'm actually going to drop netraw, and I'm going to send a ping, and it gets blocked. Operation not supported. Okay, that's because I dropped netraw. There's a syscontrol on Linux that's been there for years and years called net IPv4 ping group range. And what this says is anybody that's in group 0 to group 1000, you can pick, actually, you can pick 4 billion if you want, is allowed to create ICMP packets and send them on the network. So if I run a container with that simple flag in it, I can send ping packets, and now I don't need netraw. So I can create just an ICMP packet and send it out, which is really all that ping needs to be able to do it. So why don't we turn that on by default? All right? That didn't modify the host operating system. That just modified the network namespace inside of the container to do that. So it had no effect on the host network at all. It just did inside the container. So a new idea that we've been talking about this past week, and basically why don't we allow the images, the developer, to specify what capabilities his application needs, right? If I come out with an application, I say, all I need is to change my UID. So all I need is set UID and set GID. So if I could specify that as a label on the container image as the developer, then we could basically have the container engines look at what its default capabilities it's going to run with it, check out the ones that the admin specified. If it's a subsection, then the container engine should just allow that, right? So we could begin to specify in the container engine, developer, right? This is users never turn up security, but hopefully developers understand how their applications are supposed to work. And if they could specify in their container images that, and then we could basically have the container engines interpret that and say, hey, this application doesn't need the 14, it only needs these 2. Now, if he specified a capability that's not available, if he was trying to move to the mama bear side of the equation, then the application, the user might need to override it, or we might need to, somehow say we have trusted images, and so therefore we allow it. But out of the box, we could do this right now because we're increasing the security in the system. So SELinux. Protect it, right? SELinux is the #1 tool that has basically thwarted almost every single exploit that is broken out of Docker. So it's using process types. We controlled the breakout. Basically, it protects the file system. So SELinux, I like to say SELinux is basically what happens in Vegas stays in Vegas. And what I mean by that is all we're doing inside of the container is you can do anything you want in the container. If you try to leave the container, we're going to block you. But inside of the container, we're not blocking anything. We're not blocking access to the network. We're not blocking access to any of the capabilities. Now, the goal here is to allow SELinux is to, again, prevent breakout, but we're allowing the capabilities because we're saying another part of the kernel, like Linux capabilities that I just showed you, are controlling capabilities. The problem is SELinux is not flexible enough to be able to do a cap drop and a cap add, right? You have to generate different policies and different types. So out of the box, we allow it fairly loose inside of the container, but it's when the container tries to break out that you're protected. So the problem with SELinux and containers is usually volumes. Anybody that just runs containers with SELinux, it works perfectly until you stick a volume into a container. And when you stick a volume, mount a volume into a container, you're basically taking labels from the host and putting them into the container, and the container cannot interact with labels from the host, right? That's the whole idea of the protection. So what we have to do is you have to relabel the labels on the host. So if you use the lowercase z and the uppercase Z on the volume mount, the tool will go out and relabel the content. So if you're doing podman run varlibdb mounted on MariaDB, you could do :z and everybody's happy. The problem is in certain times you want to run containers that take huge system directories and put them into a container. So like fluentd wants to read all the logs on the system. If I do that with SELinux and tell it to relabel, all of a sudden every tool that needs to write those logs is going to blow up. So anybody that's ever tried it, right, we actually have code in Docker and Podman to try to protect you from doing that, right, to block the :z in that case. So what's the only option you have if that happens? The option is turn SELinux enforcement off or write policy. And the problem is almost no one in this room is going to write policy. So almost everybody is 740, or at least 740 for container, which is security op label equals disabled. So there's a project going on called UDISA. I hope I pronounced that right for my Czech friends here. We would call it Utica. Basically what UDISA means in Slovak is fishing pole. And the idea here is to teach a person to fish. He eats for life. If you teach him, give him a fish, he eats one meal. But basically, the idea is to help them build policy for your container. So what UDISA does is it examines a policy. You create your container like the fluentd container that I just created, and you basically have look at the volume, and I can generate policy based off it. There's a talk Sunday morning that's going to go heavily into UDISA and explaining how it works. And in this case, with UDISA, we can take things like fluentd and move them towards Mama Bear, right? Make you a little less secure on your system, but not make you have to go all the way to disabling SELinux for the container separation, right? UDISA also has the feature that it can actually examine your container and say, hey, this container is only going to use these capabilities, and then turn off, from an SELinux point of view, the rest of the capabilities. It also can look at network ports and tighten them up, so you can move a little bit towards Papa Bear for that container. So let's look at the next one, limiting the communications of the kernel. So Seccomp, processes communicating via kernel syscalls. So what Seccomp does, SELinux basically prevents you from interacting with files on the file system. What Seccomp does is actually prevents you from interacting with the kernel. Certain syscalls it blocks. So on a standard Linux system, I guess there's 450 syscalls. I looked this up last night. It's around 450 syscalls. There's actually a whole bunch more than that on an x86 64 box, right, because there's 32-bit code. So all the 32-bit, I don't know if there's another 450, but basically it's almost twice as many syscalls when you have an x86 box because that supports 32-bit code. So when I put a container into a Seccomp filter, if I add a Seccomp filter to it, I can drop the syscalls down quite a bit. I can eliminate the 32-bit syscalls, and right here, if we look at the default Seccomp file that everybody uses in the world, there's about 300 syscalls still allowed. So if you go from 900 to 300, that's pretty good, right? But can we do better? Right? Everybody in the world runs the exact same Seccomp file. Nobody changes that. And it's difficult to figure out, what syscalls does my container need? So how can we do better than the 300? So Valentin Rothberg, who's in this room somewhere, wrote a blog describing some of this technology, but he did some investigation, and he found an article by Aquasec that's saying that most containers only require 40 to 70 syscalls. I find that a little hard to believe, but if we're allowing 300 and we only need 70, we could be a lot more secure if we could basically figure out which syscalls a container needed and be able to get down to that lower number. So last summer, we had a Google Summer of Code student in here, and we wanted to use BPF to figure out which syscalls a container is running. Okay? And we created this thing called the OCI Seccomp BPF hook. And what it does is it basically watches the container with BPF. Every time it makes a syscall, it writes it out to a file. All right? Pretty simple. There's a DevConf talk tomorrow at 5 p.m. that's going to go heavily in depth into this, but I'm going to do a quick demo now and show you how it works. So this is a demonstration of the OCI hook to fire up a BPF program to trace all syscalls. So this is what the hook looks like. So it's basically an executable. You can, on your Fedora box or RHEL boxes, you can do basically a dnf install OCI Seccomp BPF hook, and it puts down a hook like this. This basically tells the container engines to launch this hook before they launch the container. Oops. Okay, so now what I'm going to do is I'm actually going to launch a container that's just going to do an ls of slash. Okay, all it's going to do is launch a container and look at slash, but I'm passing in a special annotation here that says I want that OCI hook to watch all syscalls that happen on the system. So it runs, and there, just finished running a container. And what I'm going to do now is I'm going to actually look at the syscalls that are required to do an ls of slash. Okay, so it's pretty simple. This is actually exactly what Seccomp rules would look like as a JSON file in the system. At this point, now I'm switching from using the OCI hook, and I'm actually going to run the container with the Seccomp. So now I'm locking it down to those 25 syscalls that are required to do slash on the system, and boom, it worked. Okay, so basically I recorded what syscalls are needed, and then I'm able to run it. So we're going to take a step further, and now instead of just doing ls slash of slash, we're going to do an ls-l of slash, okay? And with the same lockdown container with the Seccomp rules, and all of a sudden Seccomp is blocking some syscall on the system. All right, so now what I can do is I can go out to my auditing subsystem and see that ls-l needed these other syscalls. So basically what's happening here is it's actually attempting to basically go get UID name based on the UIDs on it, so it can reveal that it's Walsh's files or whatever, and that's actually talking to the SSS daemon on the system. So if I basically run again the syscall trace on it, I can actually show, what I'm going to show you now is, now I did an LSL, but basically I recorded the differences between ls of slash versus ls dash of slash. And what's strange down here is it actually removed one. So ls of dash L actually doesn't need stat. I don't know why. But the way you can do with the OCI hook now is you can give it an input file and an output file. So you can imagine if you had a CI/CD system that ran your application multiple times, every time it ran it with the hook, watching all the syscalls and ran through your entire CI/CD system, and you got to a point that you had a really nice Seccomp file out there. Now you could take that Seccomp file, put it out into production, and maybe continue to run the hook for a month or 2 months in production and continue to control. Basically, you'll be still controlled by the default Seccomp file, but now we could look and see if there's additional syscalls that are needed. At some point, you'll be confident enough to say, it's been running for 2 months, I haven't had a problem with it in production. Now I'm going to switch it over and enforcing. Okay, now I can start to use the Seccomp file one. So that sounds great. The problem is, none of you are going to do that. All right? A developer might do that, but no users are going to do it. Right? A user's not going to understand it, and the user's not going to understand how to do it. So what we need, oops, I'm done demoing at this point, stop demoing. So how do we ship and use these Seccomp rules? How do I ship those out? Well, in production, in Kubernetes or Podman or Docker or anything else, the only thing I download when I run an application is the application image, right, the container image. So we're proposing that we basically, when I'm developing my image, I develop that seccomp.json file, and I stick it in the image. And now we have potentially a label or an annotation that basically says IO container seccomp and tells it where in the image to use the seccomp file that's generated with it. If and only if the container image is seccomp.json is a subset of the default seccomp, basically that's what the diagram is trying to show you. So we can guarantee, if I can guarantee that the image's seccomp is just a subset of the seccomp that I was going to run it by default, and if I'm not running any seccomp by default, that means that there's no enforcing, then I could run, you know, guaranteed to be a subset. I could actually run out of the box without a user interaction or anything else. I can run lockdown. I can move you towards basically the Papa Bear. So that's, you know, one of the things we're experimenting with right now. Actually, we have pull requests going in, is basically shipping these seccomp files inside of containers image and then allowing the container engine to automatically specify the seccomp rules that will be used. User namespace security. So user namespace is really, really cool. How many people have run rootless Podman? Isn't that cool? Everybody else that hasn't run it, go back to your Linux box and try it out. You can do everything you can do in Docker without being root on the system. Okay? It is really cool. You can run your full container workflow, and you don't have to be root to run it. Don't tell me that I can do that with Docker by making the Docker socket in the Docker group. That is the most dangerous thing you can do on a Linux system. Access to the Docker socket is worse than sudo without password. It is worse than giving out the root password because there is no, it's basically a client-server operation. When I talk to the Docker socket, I can launch a full root process, fully privileged, and take over your machine. When I'm done, I can destroy the container, and Docker will wipe out any access that Dan Walsh did. When Podman runs rootless, it is running as your user. Okay? There is no privilege, there's no privilege escalation or anything else. So rootless Podman, rootless builder allows us to do all of the general container workflow with user namespace as a normal user. So rootless builds inside of a container. Imagine being able to build all these container images inside of Kubernetes in a CI/CD system without having to leak the Docker socket into the container. And these can run fully locked down, all based on the user namespace. There is an issue with user namespace that's being worked right now. User namespace requires access, it requires credentials, or your credentials to be added to a file called etc subuid and etc subgid. This right now is not network distributable. Okay, so basically there's no LDAP access to this thing or free IPA access to this thing. So we're actually working through this process that you have to, if you wanted to say had hundreds of thousands of users and you wanted to distribute etc subuid and etc subgid, we're working through the process of getting that. But basically user namespace is really, really cool for doing it. But basically that supports rootless users. So rootless users works, but when you're running all your containers as rootless user, they're all running inside of the same user namespace. When I'm running containers as root, either under Podman or under Cryo in Kubernetes, they're all running in the same user namespace. So in the perfect world, user namespace would give us separation between containers. So with Podman, you can execute a command like podman run user map UID 0 map to 100,000 for 5,000 UIDs. The next command runs the exact same UID map but uses 200,000 UIDs. So root inside of the first container is 100,000. Root inside the second container is 200,000. If I break out of the container, we have a feeling that you will not be able to attack the other containers because you are running as UID 100,000 versus running as UID 200,000. Pretty cool, right? This is what we relied on for security in Linux forever and ever. How many people in here have ever done that command? There's 2 maybe, right? It's really cool, but almost no one uses it. So we have user namespace in the kernel. We have it, but the problem is no one knows how to use it, right? And you can't think of it. So the human being has to go out and manage those UID maps. So if I set up 50 containers, I have to have some kind of tooling to figure out to make sure that I don't have overlap on my UIDs, or else from a user namespace point of view, the containers would be able to attack each other. So how do I get closer to Papa Bear? How do I get people to use user namespace to guarantee separation of the containers? Another problem with user namespace is we still have no Kubernetes support. I'm already down to 10 minutes, okay. We still have no Kubernetes support. Kubernetes support, there's people working on it, but every single release it seems to get pushed back one. So right now, Kubernetes has no concepts of user namespace, so therefore, even though I'd want to run all my containers in different user namespaces, the kubelet has to understand that, okay? And how do we work through that? One other problem with user namespace is lack of file system support. So when I run those two containers, the one that's running 100,000, any files in its file system that are owned by 100,000, it will see is owned by root. The second one is 200,000. If I take the same image for both containers, I need them shifted, right? So I want the same image mounted into one container, it looks like it's 200,000, and to the other container it's 100,000. So user namespace has been around for a long time, but there's never been any file system support. So what we've done in the container engine tools is we've actually added choning. So we have really high performance choning going on underneath the covers. So if you ran those two containers on a fresh storage block, it will actually chone the second one to match the user namespace that you're going to be running in the container, and then everything works perfectly. So we actually have some pull requests, and we've been experimenting with parallel chone. So imagine right now if you chone a file system, a fairly large file system, there's one process going through and not choning those. Imagine instead if you use parallel, in every single directory you forked off a thread, and that thread went out and choned it. So we've seen speed-ups of between 10 and 100 times by going to parallel choning. Now, as soon as people hear that, they say, well, what about spinning disks? Well, stop using spinning disks. But basically, it's a way to speed up the choning. The real nirvana of the system is a thing called the shifting file system, right? Basically get something in the kernel that understands user namespace. And this is like the holy grail. Shifting file systems, I've been asking for them for about 6 or 7 years now. And they're always 6 months, a year, 2 years away. The kernel moves at glacial speeds, and for legitimate reasons, right? This seems a little dangerous, but basically shifting file systems have made a lot of progress in the last year, but they're still not on the horizon, and I don't know where they are in terms of RHEL. So a possible solution that I am looking for is to make the container engines handle the user namespace themselves. So imagine a command like podman run user namespace equals auto, where it would go out and automatically just grab a free user namespace, range of UIDs, and actually run each container you ran automatically inside of a user namespace. So it would not become a concern of the user, and then we could turn that on by default. So podman automatically pick the user namespace per container, guaranteeing uniqueness. This is how SELinux works. SELinux guarantees the uniqueness of the container labels, and that's built into the engine. And then imagine we could add a similar feature to Kubernetes, where automatically user namespace gets picked, and everything just works on the system. So that's really what the future is. So the last section of my talk is talking about containers.conf. So earlier in the talk, we talked about all the container engines have this hard-coded constants. Right? You guys didn't even know what the default capabilities list is, right? Because that's hard-coded in the content. So we've been working on, we actually have pull requests right now, not quite merged, is the idea of taking your defaults and making them into a config file. Okay? And this config file lists out lots and lots of general configurations that you might want to set as an admin. You don't like the default config. And we'll have 3 config files for it. The one is from the distribution. So that'd be, say, Fedora just chooses to use different defaults than, say, Podman and Builder use. And then an admin can override that, and then individual users can override that. So let's take a quick look at that. So here we are. I'm just launching a container. And I just launched a container on the system, and it's using default. And you see the 14 capabilities, including that raw, on the system. Now I'm creating a capabilities file. So I created a containers.conf, And if you notice, I basically say that these, if I was the god of the world, these are the capabilities I would allow by default. And even some of these I have questionables about. But basically, I eliminated those 4 I talked about in the beginning talk. And so now I'm going to try to do a container on it. And now you'll see, so I specify containers.conf. I didn't want to install it on the global system. And now we have much less capabilities for running a container. So we went from 14 down to 10. But now I'm going to run the ping command. Oh, we lost net raw. Ping command blows up. Well, in containers.conf, I can actually add the syscontrol. So if I add the default syscontrol of net IPv4, basically the same command I did outside of the container, and now, by default, on my system, I'm running ping inside of my containers without a user having to do a single thing on the system, and it becomes either the distribution does this by default, or the administrator can override it by default, or if the user really cares about security, he can do it by default, and instantaneously he's got a more secure system. So that is the end of my quick overview of ideas we have. There's other ideas. There's things we're actually having a meeting later on with the KVM team to talk about potentially using Kata containers and how we can better integrate with Kata, which uses kernel-separated containers. But these are all the talks that I plan on going to this week, and they're all talks about containers. So at 12:30 today, we're going to actually be digging deeper into container security. We'll be talking about a lot of stuff that I talked about today, and basically brainstorming. So we have a session, and Valentine is running that session. Then we have a couple good talks on containers engine. There's a talk down here on Seccomp to go deeper into the Seccomp tooling. There's a Udica, Udica in here somewhere. And so basically, these are the talks. So at this point, I'd like to open up to any questions. Yes? Do I have any idea, basically describe, how do you figure out which capabilities? Well, see, again, in the slide about capabilities, I said I believe that we should have an annotation or a label inside of the container image that says my container will run perfectly fine with just these 2 capabilities. So therefore, by default, when you run my container, you'll use those 2 capabilities. Right. He's probably the only one in the world that's going to know. Right. He's the only one that's going to get me from Goldilocks to Papa Bear. Yes?
The syscall stuff, could you not do that potentially through static analysis? So you know the kickoff binary for the container, could you not? Yeah,
so static analysis always, I actually have a big problem with static analysis in containers, because if I static analyzed HTTPD, what's that going to tell me? Right, all I'm running is a little tiny application, right? So static analysis only works if you have a single application that only does one function or one set of functions. But in containers, we basically throw in all this crap, and so I don't know if static analysis really works. Yes?
So, do you have any ideas on how the hardware security will be worked out in OpenShift for developer users? So if the developer comes, uses an image from Hub, and the image won't run because of, for example, it needs some other capabilities. Will the debug within OpenShift somehow allow them to maybe enable more?
Yeah, so I mean, right now in OpenShift, we describe that you should never run root containers at all. But yeah, OpenShift theoretically will come back with logging and information about why the container failed. Sadly, and that's a different topic, I call it friendly EPERM. I've had open discussions for years and years about a thing called friendly EPERM, in that each one of these security mechanisms causes an application to get permission denied. And then the kernel hangs on for God life that I'm not telling you why it's denied, it's just denied. So whether it's using namespace, SELinux, Seccomp, is really hard to tell. So one of the things we've talked about there is basically using BPF filters again to basically figure out in the kernel, anytime it throws permission denied, write that to a log file somewhere that says, this container got permission denied because it was running in user namespace, or it got it because it was SELinux blocking it. Yes, way in the back. Right, so I think what you're asking is, so I set up my Seccomp filters, and suddenly the container goes down a different code path that I've never tested before. And this is what SELinux has had problems with for years, right? And I don't really have a good solution for that, except that the Seccomp, I showed you that the audit log will record Seccomp failures that are happening for your container. Whether or not there's a good mapping back from the audit log back to your container, I don't know. But basically, yeah, it's a general problem, right? And the only thing I can say is, we have to run this through as much testing as we can to try to make sure that we've got all the code paths that container could possibly run under. Yes?
What actually is recording this policy? Can I use that to record, for example, while running some tests on my binary?
Right, you basically, if you set that annotation in your OpenShift Kubernetes and have the OCI, well, that policy is going to write it out to a file. So no, you can use Cryo, you can use Podman, you can use Builder. So anything that has that capability, basically OCI hooks implement. Matter of fact, it probably would work with Docker. I'm not sure if you could get Docker to run the OCI hook. Well, you're running a container, so you have to have a tool that runs a container. Right, but I would take that binary, stick it into a container, and then run it. Anybody else? Yes? Well, I overstated. Everybody's using rootless as your user namespace. Yeah. Well, that's what well, there is. So right there is how you would choose a user namespace mapping. Well, so right there. So the idea, right now this doesn't exist. This is Dan and Fairyland. So right now, podman run / user namespace equals auto would automatically generate a secure container for it. Now, if you take that with containers.conf, you could set that up so it automatically happens for every user namespace, so all your containers would run it by default. Okay, anybody else? Yes? Right, so our goal is to work through the OCI to get this to be a standard. Right now, our goal is actually to prove we can do it. So once we can do it, then we're going to go through the standards body to attempt to get other container engines to adopt this principle to running. Right, but I would say that Kubernetes upstream and most developers don't care about security, right? It's very low on their priority list. So we will try to push it through, but we will see what happens, okay? Am I out of time? I still got anybody else a question? Yes. Right. Well, yeah, right now we populate the Etsy password based on the UID that you're coming in as. So we can populate inside the container runtimes if your entry, so if you come in and say run is 900,000, we actually add an entry to the Etsy password file inside of the container saying this is 900,000. But we don't know your username. I don't think that information is available to us when the container is run. But that would be a nice enhancement to OpenShift and Kubernetes to be able to pass down, call this Dan Walsh as 900,000 inside the container. There's a feature to set up the UID map so you can do reverse UID map, but it doesn't identify your name inside the container. So it would just say you're 900,000, right? Yes? It's just something that makes Seccomp for a socket. So Seccomp enforces syscalls. Well, that would be SELinux. So SELinux would control whether two processes can communicate together over a socket. That's what SELinux does. Yeah, that's what SELinux does. So there's no other tool other than SELinux that does that right now. Because you have to identify both ends of the socket, and with SELinux, you do it with types, okay? All right, thanks everybody for coming.